Hi, good evening, everyone, and welcome to yet another day of India's largest virtual science festival. India Science Month Online is a month long celebration of science and technology, and we have invited scientists, researchers, educators, science communicators, students, and all science enthusiasts to come together on this platform to collaborate and celebrate the wonders of science and technology. This is our initiative at bringing together science and society, for we truly believe that science has to be more accessible to all. In our attempts at making science more accessible to the public, the theme that we have chosen for this year's fest is space, healthcare, and robotics. We have a number of talks, panel discussions, workshops, demonstrations, and online games themed around these. And we also have topics on science. Also have events on science communication and general science to make the event more inclusive and interesting for all. We are streaming our events live on social media, and we have a number of people who have joined us on Facebook. So we really are very excited about our events, and this is the last week of the festival. So do make sure that you invite your friends and family to join us, because the festival is free for all. All you need is an internet connection, and the best researchers and scientists from all across the world will be on your screens, and you will be able to questions, and you will be able to hear about their work on very close quarters. Sorry, my internet was creating a little bit issue, but our festival has a number of social media competitions going on. We have a Twitter contest wherein we are inviting all our attendees to tell us about the favorite aspect of the talks and panel discussions that we are putting up. So all you need to do is take a screen grab of whichever event you're watching, and just tell us what you liked in particular about that event, and we'll make sure that the best tweets come to everybody's attention and also win exciting prizes. Like I mentioned, this is the last week of our festival, which is on till the 31st of January. Our festival has events for all age groups, starting events for 3-year-olds, and going up to adults who are interested in all aspects of science and technology. The upcoming events for today and for the weekend include talks on search of life in space, talks on science communication, science archiving, nanotechnology in healthcare. Um, we have an interview with an astronaut, and it just keeps getting exciting. So make sure that you tune in for all our events. So today we have a very exciting session with one of the most well-known researchers and science communicators from the world of space sciences. It gives me immense pleasure in inviting Dr. Daniel Angerhausen, who's going to be talking to us about his work and his research in space sciences. And before we begin our session with Dr. Angerhausen, I'd just like to know a little bit more about the attendees that have joined us. So, if I could please request you to answer the polls that you will see on your screen at the moment. We'd love to know a little more about our attendees. All right, so the results on my screen tell me that maximum audience members are college students. We have a few faculty members and some professionals working in tech. A few are also from life sciences, and we don't have many professionals working in the field of space. So clearly, this is an audience with a very, very different, we have a very varied background amongst our attendees, and that just makes the event even more exciting, right? So, if you could just answer the second poll that you see on your screen. All right, the results on my screen tell me that most of our audience members know a little about the topic that is going to be discussed today and have read about it somewhere. Some of our audience members are studying this and wish to pursue it further. And a small portion of our audience members don't know much about the topic but are curious to know more. So, like I said before, it looks like we have a good mix amongst all our attendees, and that's just going to make this session more exciting. The best part about today's session, not only do you get to hear Dr. Angerhausen talk about all his research in space sciences, but you also get to attend 20 minutes of a closed meeting session wherein you get to ask him questions yourself. Dr. Angerhausen has very kindly agreed to be a part of our post session interaction, wherein he will be speaking to some space enthusiasts. So, for those of you who are interested in speaking with him, do stay tuned. Towards the end of the entire webinar, we'll be putting a link for the meeting room in the chat box, and all of you will have access to it. We have very limited numbers that will be allowed into the meeting room. So please make sure that only those who are really interested in asking him questions related to space sciences come into the meeting room. And with that, I would like to invite Dr. Angerhausen to please turn on his video and audio. For all our attendees, Dr. Angerhausen is an astrophysicist and astrobiologist at ETH Zurich. He's a former NASA postdoc and has done a lot of science communication, and is the founder of Explainables, where he's training upcoming science communicators. And he has uh, been working in the field for many, many years and is a core science committee member, mentor, and facilitator at NASA's Frontier Development Lab. Sir, it's such an honor to have you here with us today. It's an absolute pleasure, and I think all our attendees are super duper excited to hear more of you. So, I think we will just, if you could just begin the talk by sharing your screen, we're all set to hear you talk.
Sure, yeah, thank you very much for the invitation. I'm similarly excited to be virtually in India today and tell you a bit more about my research. And not only my research, but in general, an introduction to the field of astrobiology and how we hopefully going to find life in space. So this talk, as you've heard in the announcement, is going to be about aliens, exoplanets, and this field of astrobiology and how we search for life in space nowadays. And you've already heard my introduction, so I won't go through all these affiliations, all these companies that I worked for or with in the past, but I just wanted to acknowledge, in which institutions and which contexts the research that I present is done. By the way, I'm the guy on the left side here. This is a Neanderthalian, which is kind of interesting because I'm originally from Germany and grew up very close to Neanderthal. So I leave it up to you to figure out where this similarity comes from. Okay, so astrobiology, what is that? So this is, this might not be a familiar term for all of you. So I thought I start with really explaining a little bit more what this whole field of astrobiology is about. And when I do this in my talks, I usually start with a story that some of you might be familiar with. I'm not sure, it might even be an old legend from India, maybe from somewhere in South Asia. So it's the legend of the blind man and the elephant. So the story goes that a group of blind men find an elephant and want to find out what this thing is that they just found, right? So the one of them touches the tail and tells the others, well, for me, it's like a rope with some sort of brush at the end. The next one is touching the leg of the elephant, and it's like, okay, for me, it more feels like the trunk of a tree. The next one is touching the side of the elephant and says to the others, I don't know what you're talking about, but for me, it's more like a rock. So all of these blind men have a different perspective on this big thing of an elephant, and it's really similar to us in understanding life in space. There are so many aspects: geology, biology, chemistry, astrophysics, and I will show you even a couple of more other fields that are really involved in understanding this big question of life in space. So in a sense, this life in space is like this elephant, and none of us blind scientists in our field can understand the whole thing. We really have to communicate with others, with each other, look at different aspects of this phenomenon that we call life to really understand this big elephant. And I guess all of you, or many of you, got really caught by the title and want to hear about aliens. So I thought I start with, showing you actually some images of aliens, and not only aliens from space, aliens that actually live down here on Earth. And we call them extremophiles, and in a second I'm going to tell you why we call them extremophiles. So the first example is this blobfish here. I think in 2015, 2016, it was voted the world ugliest animal, which is actually kind of unfair, because the blobfish looks much, much better in its original habitat, which is about 6,000 meters deep in the ocean under really, really, really super high pressures. And it only looks this ugly when you take it out of the ocean and put it at, room temperature, room pressure up here on the land. So it's actually not that ugly in its original habitat. But the thing about the blobfish is, as I mentioned, it can survive really, really high pressures, really, really deep down in the ocean. And this is some sort of an habitat, some sort of a biotope that we could also expect, for example, on Europa, like an icy moon in our solar system, where under the thick ice, there could be an underwater deep ocean where something like a blobfish could eventually survive. So this is why, by studying the blobfish, we could also study and learn a bit about how life could be in these subsurface oceans on icy moons in the solar system, for example. Another example from Earth is the icefish. So the icefish, as the name suggests, lives in really, really cold regions, so in the Arctic regions, and it can basically thrive under temperatures that are close to freezing. So it survives at 0 degrees Celsius, which is technically the freezing temperature of water. So it really can survive super, super, super cold extremes. And this is why all these animals are called extremophiles, because they love the extremes. They can survive in extreme conditions. And again, these conditions could be similar to somewhere else in the universe, where life could also be present on a very cold planet, for example. Similar on the other end of the temperature scale, this is the Pompeii worm that thrives and lives and reproduces really deep down in the oceans, where you might have heard about these underwater volcanoes, so-called black smokers, where you have like really hot, in this case, basically close to the boiling temperature of water, these underwater steam events. And this is where the Pompeii worm lives. So the Pompeii worm lives at the other end of the liquid water scale, right close to the boiling point, and can thrive at these temperatures. So life really can survive under all very extreme conditions here on Earth. And by studying this life in these extreme conditions here on Earth, we can learn a lot about how life could look like out there in space. And I leave you with this last one. This one actually even looks a bit like an alien, maybe from the movies. And I leave it up to you as your homework to maybe Google that name and figure out what that animal is. And a little hint, the extreme condition that this one is living is actually inside of humans. So there might even be one or two in the audience who have one of those inside of them. So maybe you want to look it up on Google and figure out where in which extreme conditions this alien is living. My favorite of these aliens, of these extremophiles, is the tardigrade. Maybe some of you have heard about it. It's called the water bear also. Looks a little bit like this, tiny little gummy bear you can see here, swimming, cute little thing. the cool thing about the tardigrade is as soon as it gets dry, if it's not in water anymore, it can put itself into some sort of a cyst state. So you can see that on the bottom left here. It puts itself in this shell, almost like a turtle, or a really thick shell. And this cyst state, this hibernation state inside of this shell, it can withstand gamma radiation. It can survive without oxygen. You can put it into liquid helium and then put it into super hot water, and it will just survive. It really can sustain sometimes up to 10 years or more in this cyst state. And in this cyst state, it would basically be a perfect astronaut. So if you could build a spaceship or could build a spacesuit for humans, it would probably be best made out of this material that the tardigrade's cyst is made of. So in a sense, this makes kind of like a miniature astronaut. So this tardigrade could really survive space much better than humans could survive. And again, this is something we study as astrobiologists, study these extreme animals, these extremophiles, to learn about life in space in general. So this is why these extremophiles coming from biology are a big part of astrobiology research nowadays. Then I also want to briefly mention some really other aspects that are also part of the astrobiology research. Maybe some of you have read this quote from So Long and Thanks for All the Fish from The Hitchhiker's Guide for the Galaxy. You should really read that. And I'm referring to this because sometimes, when people hear that I work for NASA, they're like, oh, you probably have aliens there in a hangar, and you probably talk to aliens every other day when you work there. Usually what I answer is, the thing is, we can't even really communicate with the next intelligent thing on our, right? So maybe chimpanzees or dolphins or gorillas, like really other intelligent beings on our planet, we are not really able to communicate. Maybe some people think they can talk to their dog or can talk to their cat, but we really didn't even establish a form of communication with animals on our planet that are made from the same DNA, breathe the same air, drink the same water. So why would we even think we could communicate with aliens, right? And this is also actually a part of Seti research, the search for extraterrestrial intelligence. Some people really study how animals communicate in order to maybe learn from that how we eventually could be communicating with intelligent aliens out there too. So this is also a part of this very diverse, very multidisciplinary field of astrobiology, to look at this, linguistic side of how could you communicate. And there's also sociologists who think about what could happen to our societies if we find life in space. So it's really, really, as we call it, a multidisciplinary field of research, people from very different fields coming together to answer this big, big question of life in space. So now the question is, so what am I doing, right? What is my part of it? I'm certainly not a linguist, or I'm not really much, don't have much background in chemistry or biology. So I am, used to say, so I'm an astronomer. So my background is in astronomy, and always joking, I like to climb high. As an astronomer, as an astrophysicist, we like to get high. That's kind of like the joke. And what I mean with this, that we like to build our telescopes, for example, high in the mountains. So here you can see the younger version of me when I was, right before I started, or right when I just started my grad studies, at some of the best telescopes in the world. So the telescopes in Hawaii and Chile are really two of the best places in the world to have these telescopes, very high on top of the mountains, where we have the best observing conditions to look outside our planet. And if you want to get really high, if being on top of a mountain is not enough for us, we also build telescopes on satellites that really go into space and observe from there. And two examples here are the Cheops telescope, the characterizing exoplanet satellite that was actually built here in Bern in my old institute. The lab was literally one in the basement under my office. And the other one is the James Webb Space Telescope. Maybe some of you have heard about it. It's the next generation so-called flagship mission by NASA. Some of you might have heard about the Hubble Space Telescope. So this is basically the next generation big telescopes in the size of, or the class of Hubble, really a new biggest telescope for a generation that will be launched by NASA hopefully this year. And here again, I brought you an image just to get an idea of the scale. So this is me in the clean room, which was before Corona, so I wasn't wearing that mask for any other reasons than keeping this laboratory where we built the telescope really, really clean. This is why I was wearing this so-called bunny suit and then the face mask and everything. And you can see this tiny little mirror in the end, 30 centimeter diameter. This is really a relatively small space telescope that still can do amazing science, the Cheops telescope. We just published a paper, I think 2 or 3 days ago, about a system of 6 planets that we partly characterized with this Cheops telescope. And then on the other side here, you see this 6.5 meter super, even as a ground-based telescope, it would be ginormous, big James Webb Space Telescope. Again, behind this wall, it's a clean room. You really want to keep those clean, that there are no fingerprints and, you know, beard hair or anything on the mirror. You really want to keep them really clean in these clean rooms. And this is in the background, the biggest clean room in the world, I think, or one of the biggest at NASA Goddard, where I used to work before. And this thing is really 6.5 meters, almost the area of a tennis court. It's made from gold-coated beryllium. That is why it looks like this. And this James Webb Space Telescope is actually so big that it doesn't really fit into a rocket. So you can see here on the side, this is the Ariane 5 rocket that is supposed to carry the James Webb Telescope into space. And if it's fully unfolded, it doesn't really fit the rocket. So what the engineers did for James Webb was to elaborate this, unfold this telescope in space. So it's really wrapped up to fit in this tiny fairing of the rocket. And then once it's in space, you see here the animation going on. It will slowly but surely unfold. All these mechanical steps will go to unfold the telescope in space. So this is really, I'm always joking, like a transformer. Maybe some of you know the transformer toys. You know, you have a car and then it unfolds and becomes a robot, or the other way around. So almost like a transformer, the James Webb Space Telescope unfolds itself. And this whole process that takes about a minute in this video actually takes a couple of days, maybe even a few weeks, I think, in reality. So once we shoot the James Webb Space Telescope in space, we still have, you know, a couple of days, maybe weeks, you know, to sit and be nervous, to hope that all these different parts, all these different mechanical processes to unfold the telescopes really work out. Sorry. So then the question is, why are we getting high, right? Why are we building our telescopes on the top of mountains? Why we are building telescopes on satellites? What is the real reason, right? So sometimes people guess, yeah, maybe it's to be closer to the stars, but that doesn't really make a difference, right? If something is millions of light years away, it doesn't really make a difference if you go like 1 kilometer or 2 kilometers closer to it. So the real reason why we build telescopes very high up or even in space is a thin layer that you can see here, the layer of the Earth's atmosphere. Because you can imagine, if light comes to us from space, it's traveling through all this, you know, vacuum, basically empty space for years, right? If it's 20 light years away, it flies for 20 years through nothing, right? Cruise mode, like the highway, nothing happens, no traffic jams, nothing. And then on the last, you know, few kilometers, the light particle that comes to us hits the Earth's atmosphere, and then all crazy things happen. It gets distracted by molecules in the air, it gets reflected, all kinds of things could happen to the light when it enters the atmosphere. And this is why we want to go as high up in the atmosphere to avoid all these perturbances, all these problems that the light happens to the light when it enters the atmosphere. So this is really the reason why we put our telescopes high up in space and high up on mountains. And this is really even more complicated if you look at different wavelengths. So different colors of light, so to say, also light that we can see with our eyes. Maybe some of you have heard about ultraviolet light. You may have heard that the ozone layer absorbs most of the ultraviolet light. You can see that here about, you know, up in the ozone layer, the UV light gets absorbed. This is why we don't get instant sunburn if we go out. The problem then, however, is if you're a UV astronomer, so if you're interested in the UV light from the stars, this light doesn't even go through the ozone layer, right? So that means if you want to look at the UV light of a star, of a planet, you have to build a telescope that is basically above the ozone layer. And this is a different, light in different wavelengths goes into the atmosphere at different stages. So the only light that really goes to the ground is this optical light and the radio light. So those are the only sorts of light, sources of electromagnetic radiation that really penetrate the air. And therefore, it's not really a coincidence that our eyes work in the optical, that our phones and our radio, telephone, everything works in radio, because these are really the only ways to send information through the atmosphere. Everything else eventually gets absorbed in the Earth's atmosphere, gets absorbed by the air, by the water, that is the humidity. All these things absorb light, absorb radiation. So now in this illustration, you can see again the optical light goes to the ground, radio goes to the ground. Most of the other light gets absorbed somewhere high up in the atmosphere. And then you can see here that the infrared light, so this part of the light that is right behind the red light, some know that maybe from heating lamps. That's why also it's sometimes called the warm radiation, the infrared radiation. This penetrates in some wavelengths up to the altitude where planes fly. So the infrared light goes up to 10 kilometers and gets absorbed up there in the stratosphere. So then people probably think, yeah, okay, this plane, they just put the plane in this animation, or the plane in this diagram to illustrate how high up in the air the light is penetrating. No one is so crazy and builds a telescope on a plane, right? Well, wrong. There is actually such a thing as a telescope on a plane. So this is called Sofia, the Stratospheric Observatory for Infrared Astronomy. You can see here, it's a Boeing 747, which has this basically a garage door on the back that opens, and then you have a telescope in the back. And when I was a student at Cologne University, one of my biggest dreams was to eventually build an instrument for Sofia, which was at that time built at Cologne University, maybe fix a screw or two on something that eventually flies on Sofia. So that was my biggest dream when I was a student, to somehow get involved with the Sofia program. And today I'm standing here, 10, 20 years later, and can actually report that myself was flying on Sofia. So not just my instrument, not just my screw that I fixed on an instrument. I was personally flying on Sofia for 6-7 times by now. Here you can see us flying over the Grand Canyon. This is us observing. So it really looks very different from a typical plane inside. So everything is really refurbished, rebuilt to fit this telescope inside of this plane. So here again, a picture of me with the telescope that you again get an idea of the size. Obviously, Sofia is exactly the size of a plane. For those of you who still don't think Sofia is cool, I have 2 more things to prove that Sofia is really one of the coolest things we have in astronomy. One is Sofia has a playing card. So my little nephew, 11 years old, I think that is what he thinks is the coolest. He loves to play this, card matching game with me, and he thinks it's so cool that the plane has its own card. And then the ultimate geek cred actually is that Sofia had a little cameo in the Big Bang Theory. So here in the back, you can see a little model of Sofia behind Sheldon. So it even had a cameo in the Big Bang Theory. So I think it doesn't get cooler than that, right? Okay, so what is it that I observed with Sofia then? And this comes back to this last word in my title, the exoplanet. So I am an observer of alien worlds, so-called exoplanets. So right now, I think this number is not super up to date. Right now we're even at more than 4,000 of these planets outside of our solar system. So extrasolar planets means these planets are not around the sun, not like the planets in our solar system that we know, but around other stars. And right now we know about 4,000 of them. And that sounds easy, right? So that sounds easy, but actually the first folks who found an exoplanet here, Didier Queloz and Michel Mayor, 2 colleagues from me from Switzerland. I meet them all the time. I work with them once in a while. They got a Nobel Prize for that. So it was such a big deal to find the first of them, the first of these 4,000 about 25 years ago, that they got awarded the Nobel Prize for Physics just last year or 2 years ago now. And to illustrate you how hard that is and why it's such a great challenge, such a great accomplishment to find those, I brought you another video. So this is real data. So this is actually Mercury transiting the sun. So you can maybe see this little black dot, and if not, it's not a problem, but you see this really tiny black dot moving over the sun here. So this is actual data from a solar telescope, the solar telescope by NASA that looks at the sun while Mercury is transiting between us and the sun. So very sometimes we are so lucky that Mercury moves between us and the sun, and then you see this little tiny black dot going in front of the sun, and that gives you an idea how hard that is for us. So if we want to find planets around other stars, we are looking for these tiny little black specks next to these ginormous big glowing balls of fire. So this really, really shows you how hard it is and why it was such a great accomplishment for my colleagues to find the first one, and that it's still a big accomplishment to find all these 4,000s, because that is a really tough challenge to find these much, much smaller things next to these much, much brighter and more active stars. But this video does not only illustrate the challenge, so the size difference and how hard it is to find them, it also shows an example for one of the methods we use to find these exoplanets. Because sometimes we are lucky, and not only Mercury transits between us and the sun, sometimes we also find other planets transiting in front of other stars. So here you can see an example of a Jupiter going in front of the star like the sun, and then you can see why this planet is moving in front of it. The brightness of the stars goes down for a bit, and then as soon as the planet disappears from the disk of the star, it goes up again. So, and by observing these reoccurring dips in brightness again and again, every time the planet orbits the star, the light of the star goes a bit down and then up again. By observing this almost like a heartbeat, again and again and again, we see these dips. We can see that there's a planet around the stars just by these reoccurring dips in brightness. And that is exactly what I observed with Sofia. So these dips in brightness were one of the things that I used to study. And here you can see my team that did the very first exoplanet transit observation. So that's how these occultation observations are called. October 1st, 2013. Here you can see my team inside of Sofia. I'm the guy in the corner, the only one who's kind of happy, while the rest was, more or less, I guess, a little bit upset that I had to work for me, or they just want to go home after the observation. One thing that I really want to point out here, especially for the girls in the audience, so on this mission we flew, the mission director, one crucial telescope operator, and one of the instrument scientists were women. So really don't let anyone tell you that girls can't work for NASA or that girls can't be scientists. So on this mission, on this very important observation, some of the most important jobs were done by women. So really don't let the boys tell you can work for NASA. This is proof that at NASA and in astrobiology especially, everyone works together and there's really room for everyone. So don't let the boys tell you can't be a scientist. So, and this is the observation. So this is how the actual data looked like. So as I mentioned before in this video, we observed the brightness of the star, and then the brightness went down a bit while the planet was passing in front of the star, and then it went up again, and then the star was back to the original brightness. So this was the first observation of such a transit from a plane with Sofia at that time. And this is a little tweet that I made next morning. So also for those of you, not just the girls and also the boys who want to work for NASA, the first thing you got to learn is the thumbs up. This is, in the morning when your mission worked out, you have to post a picture of yourself putting the thumb up. So everyone should, exercise that right now and put your thumbs up. Okay, so what kind of planets are those that we observed there, right? So one of the coolest things I think that we figured out about these exoplanets is that most of them are super, super different from what we know on Earth, actually. So for example, the planet that I observed at this observation was a so-called hot Jupiter. So those are planets the size of Jupiter, but very, very, very close in. So even closer than Mercury is in our solar system. That's why they are super hot. So some are thousands, 1,000, 2,000 degrees Celsius hot, very, very close to their stars. So this is a class of exoplanets that we don't know from our solar system, but that are kind of, once in a while they actually happen out there. So this is a class of exoplanets we had no idea before that even existed. Another interesting question that we are working on right now is this, what we call the super Earth versus mini Neptune paradigm. So we actually found out that most of the planets out there, most of these exoplanets, fall into a box right between Earth and Neptune. So this in the solar system, you see behind me here, all the planets in the solar system. We really got just two classes, like the rocky, smaller ones, Mercury, Venus, Mars, Earth, close in, and then the bigger ones, Neptune, Saturn, Jupiter, farther out. And there's nothing really intermediate size between Earth and Neptune. However, for the exoplanets, one of the class that we find most of is this intermediate size. And now we want to understand, this intermediate size. Are these just, grown-up Earth planets, really big rocky planets? That's why we call them super Earth. Or are they just shrunken down Neptunes, small ice and gas giants that are just smaller than Neptune? So this is one of the questions that we're trying to figure out right now. Where is the transition region? When does a rocky planet become an ice giant? And all these kinds of questions. So this intermediate class is also one of the questions that we are tackling right now. And then coming back to the big question that I raised in the beginning, obviously the big question that all of us want to eventually answer is, can we find life on some of these exoplanets? And one thing that we are looking for are so-called biosignatures. So certain gases, certain spectral signatures in the spectrum of these planets that can tell us maybe a story about life on these planets. And one, maybe the most promising and one at least illustrative example is if you find oxygen and methane at the same time in an exoplanet atmosphere. That's what we think is a pretty good sign that there might be life. And the comparison that I always do to find oxygen and methane at the same time in an atmosphere is similar to finding students and pizza at the same time in a room. Because if you have students and pizza in the room, what happens? Well, the students eat the pizza, right? It takes 10 minutes and the pizza is gone and the students are still there. And it's similar for oxygen and methane. They are chemically so reactive. If you put oxygen and methane in the same room, they will chemically recombine and usually either oxygen or methane remains. So if both are present at the same time, if pizza is present in the presence of students, someone has just delivered the pizza, right? Otherwise, they would have eaten it up. And this is why we think if we have oxygen in an atmosphere and there's also methane, something has just produced the methane. Otherwise, you wouldn't find it at the same time. And then we think this could be a strong hint, so-called smoking gun, that there's life on this planet that constantly produces this methane. So always think about, this comparison, grad students and pizza, oxygen and methane. If you find both at the same time, something interesting is going on, or something has just delivered the methane in that case. So this is why this could be a good biosignature for us to find both of these molecules at the same time. But the problem is, a planetary atmosphere is not just, some gas and the biosphere interacting, right? So there are, northern lights, there's ice, there are oceans, there are volcanoes that put stuff in the atmosphere. There's interaction between the oceans and clouds. There are rivers that get, material out of the crust into the air. So there are so many different processes that put molecules in the atmosphere that we observe, right? There could be a volcano that put the methane that we thought was from life in the atmosphere. So this is really coming back to this big question of the elephant, right? So an atmosphere of a planet is like this atmosphere, like this elephant. You need people who know about ice. You need people who know about volcanoes. You need people who know about northern lights. You really have to combine the expertise, just like the blind man had to combine the different parts of the elephant. We have to combine the different parts, chemistry, biology, geology, that contribute to an Earth atmosphere. So this is a typical example for astrobiological multidisciplinary research, combining these different fields, the knowledge from all these fields to eventually answer this big question. So coming to an end, I just want to give you a little, one of the coolest things that I think we found out so far is that in our neighborhood, so the stars around the Earth, the other stars in our neighborhood, we found out that between, let's say, 5 to 10% of them do have planets that are similar to Earth in terms of size, in terms of temperature, and therefore could be possible habitable for life. So we can't tell right now if they really do have life, but at least they have the right size, the right temperature. There might be water there, liquid water, to at least have, you know, some of these extremophiles I showed in the beginning. So 5 to 10% of the stars in our neighborhood have these conditions. Of the planets in our of the stars in our neighborhood have planets that have these conditions. So next time you go out, you know, go up in the mountains, look at the stars, start counting, count to 5, count to 10, count to 20. So, you know, between every 5th to every 10th, maybe every 20th star up there could have a planet that hosts life. And I think this is really, really crazy to know, or really, really great. You know, one of the greatest things that we figured out in the last 20 years, a completely unknown question just 20 years ago, that these planets like Earth are actually pretty common in the universe. And with the next generation of telescopes, and this is what I'm working on at the moment, it's the so-called LIFE mission. It's also an acronym. It stands for the Large Interferometer for Exoplanets. So you can see here, it's actually an array of telescopes. So it's not just a single telescope. It's a bunch of telescopes. In this scenario, we would have 4 different telescopes and 1 combining telescope or combining spacecraft that combines the light from these 4 telescopes. And without telling you too much about the technology that is behind there and all these, you know, little scientific tricks that we do, this telescope should be able to observe, you know, about 50 of these Earth-like planets in our neighborhood to really figure out if there's life or not. And this is what I'm working on right now. And it's really the big goal and the big dream of my career, to be part of the team that eventually builds this telescope and eventually answers this question. You know, is there life? Is there any kind of life, any oxygen and methane in these planets in our neighborhood? So to summarize, we are really the first generation in history, really, that has the technology, or at least, you know, in 10, 15, 20 years, depending on, you know, political decisions to fund science or not, we are really the first generation in history that can answer this, you know, historic, old, biggest, maybe one of the biggest questions of humanity: is there life in space? So we are really, for the first time in history, have the chance to answer that question, to figure out if these planets in our neighborhood are more like Mars or Venus, or really these nice little habitats like the Earth is. So this is really the biggest chance for our generation. And if you're a student right now, you could be maybe, you know, a bit too old and it takes a little bit longer than I hope to get these telescopes. But if you're a young student now, you could be at least the generation that answers this question. However, we are not just the generation that has the chance to find life out there in space. We are also the generation that has to face this big challenge to keep this one planet Earth that we know has life, still a habitable planet. So I think besides having the opportunity to find life in space, we also have the big challenge of our generation to keep this planet from the worst climate change disasters that are coming up there. So with that, I want to close my talk, and I'm looking really forward to some questions from you. Thank you.
Thank you so much, Dr. Angerhausen. That was absolutely fantastic. Such an interesting talk to listen to. It was such an absolute privilege to be a part of the attendees. I think all of us really enjoyed the visuals that you showed through the course of your talk. Thank you so much for putting all of these together. And I think my favorite takeaway from the talk was, anybody aspiring to be to join NASA, just make sure that you know how to do this, because that's super important. That was really lovely. Thank you so much for telling us about all your research. And we have a lot of questions that are coming in, and I'll be asking you a few questions in this webinar. But I just want to tell all our attendees that we are going to host a small closed meeting room interaction with Dr. Angerhausen. So those of you who are interested in having in asking him questions, make sure that you stay till the end of this webinar. We'll be posting a link in the chat box, and there are very few number of attendees that we will be allowing into the meeting room, and ISF reserves rights to remove anybody from the meeting room. So just make sure that you're quick to click on the link and join us in the webinar room. So sir, the first question that we have for you here is, um, why do we need to find life on other planets? So what drives the motivation of looking at life on other planets apart from Earth?
Yeah, that's a good question. So I think, I mean, one thing that I mentioned already, I think it's like one of the oldest mysteries of humanity. I think it's really, I'm always joking, like probably the first humans, when they looked in the sky, eventually they started asking themselves, are there other planets? And if so, are they like Earth? So it's maybe nothing that gives us, some sort of profit, or, we might not be able to get, the Teflon pen out of it, the classic example. But at least for me personally, it's really this motivation to be part of the team that answers one of the biggest, almost philosophical questions, almost religious, maybe even questions of humanity. So this is what drives me personally. But I can understand people that think, I don't really care if there's life outside there. And for those, I can tell you, there's always also like people are criticizing, you built this telescope and it cost $1 billion, couldn't be used it for other things. So I guess maybe this question is also coming from that direction. So what I usually answer to these questions is, first of all, if we build a telescope like that, it's not that we just shovel $1 billion on a rocket and make a big firework, right? This $1 billion is invested on the ground, right? So this is invested in grad students who might work on this telescope for 4 years and then go into the industry. It might be invested in industry partners who develop a technology for this space telescope that then eventually is going to be used at SpaceX or Hyperloop or some other company. So it's really both of these, right? So on the one hand, we are answering some of really basic scientific questions that don't really have any sort of like profitable meaning, but it's really, at least for me, a big philosophical question. But on the other hand, really by solving these problems, we solve a bunch of other problems at the same time, and we educate a whole generation of researchers, scientists, engineers that might go into other directions. So I hope this kind of like answers your question.
Oh, absolutely. I do think it's got, like you rightly mentioned, it's a good mix of, the scientific process, a personal interest in the field, maybe answering philosophical or religious questions. So I think it's a mixture of a lot of different things that might motivate a scientist to pursue the aspect of life on other planets. That was very well said, sir. Okay, so the next question that we have, so how can we successfully create a habitable planet? And I mean, how do we go about sort of making sure that the planet is ready for humans? How would we go about doing that?
I mean, if it's ready for humans in terms of going there and colonizing there, that is probably something that is very, very far in the future. So the distances in space are just like ginormous. So even if you go at the speed of light, which is most likely the total speed limit here, it would take 4 years to get to the closest planet or the closest star in our neighborhood. So for those of you who like to chat or WhatsApp or signal with other people, if you have a friend on Alpha Centauri and you send them a message, it takes 4 years to get the message there, and it takes 4 years to get the message back. So it's nothing for impatient people. So, and then you can imagine it also takes, even if you have the speed of light, it takes you 4 years to get there. So it still takes probably generations to get technology to even get to these other planets. And there are also plans to go to Mars and maybe terraform Mars, but it's really orders of magnitude. And this comes back to my last slide. It's orders of magnitude easier to keep the Earth a livable planet than trying to make a livable planet out of Mars. So we should really focus on, getting climate change under control and, make sure everyone gets clean water and everyone, no one has to be in poverty and be hungry on the world. And these are much easier problems to solve than terraforming Mars. So I think, and once we got everyone fed and everyone water and everyone breathing, then we can maybe start thinking about colonizing Mars. But I think those are more important priorities. But then I still think, coming back to the question before, that this can still be inspiring, right? So that doesn't exclude each other. Right, so one could actually take this as a motivation to make the Earth a better place before we go out there, right?
Absolutely. So that was so well said. I think a lot of our researchers and scientists who are working in space science that have joined us for this festival are absolutely stressing on the fact of how much we need to take care of our own planet before we can even think of going to another. And that leaves a very good positive message, I think, that our focus has to be on taking care of our planet. And that leaves a very important message for all of us. I'd like to tell all our attendees that Dr. Angerhausen is very, very active on Twitter. So we've linked his Twitter handle on chat. So make sure that you go and follow his work over there, and his website is also mentioned on chat. The next question, sir, that we have for you here is: Have you had any? Have you done any work with SETI? And how has your experience been, if at all you have had the opportunity of interacting with SETI researchers?
Yes, so I actually worked a couple of times actually at the SETI Institute in California. So SETI, for those who are not familiar with it, is the Search for Extraterrestrial Intelligence. But in fact, the SETI Institute itself also works on all things astrobiology. So not necessarily just radio, listen for radio signals from other planets, from other stars, which some of you might have seen in the movie Contact, for example, that was made about Jill Tarter, which is also a very big, famous and very inspirational scientist at the SETI Institute. So yeah, I work there, and I also have like a tiny, pet project, so to say, also in the search for extraterrestrial intelligence. So what I'm currently working on with some colleagues is we look at images of the moon. So you might have heard there's like an orbiter around the moon that takes really terabytes of imagery of the lunar surface every day. And there are actually pictures, you can Google it, of the lunar landing site. So amazing images. So really, that's very inspiring images. You can see images of the Apollo landing sites with tracks of the footsteps, and you can still see the landing stages and the missions where they had these lunar cars. You can see, the tracks of the lunar cars. So what we did was, or what we're working on right now, is training an artificial intelligence to identify these landing sites in these terabytes of data. So there are terabytes of lunar data, and only very few have these Apollo landing sites and other, stages and rovers and things that landed on the moon. And once we have trained this artificial intelligence to identify the Apollo landing sites, we can check what else it finds. Maybe it finds a crashed UFO or an ancient pyramid or a monolith or something like that. So this is kind of like my little contribution to the field of SETI, just to find these anomalies on the moon and see if maybe some of them are some remnants of extraterrestrial intelligence. And actually we now rebranded it. It's called kind of like technosignatures now. So this whole research of SETI is now kind of like rebranded and renamed, and it's looking for technosignatures similar to these biosignatures. So signatures of life. We are now looking for technosignatures, signatures for technology outside there. And last but not least, just I want to mention, there was really like a paradigm shift in the community. So 10, 20 years ago, it was still kind of like, a taboo topic, and you were kind of like, a crazy person wearing an aluminum foil hat if you were doing SETI research or technosignature research. But now, especially because we know there are so many planets out there, as I mentioned, 5 to 10% of the stars have planets like Earth, we can really legitimately start thinking about, there could be civilizations. How long would a civilization survive? What kind of frequency would they message us? So these are really legit questions to be asked in research right now. So it's definitely not a fringe topic. Sorry, I'm going very, very far from this my answers.
No. That was very, very insightful. I do feel that. Um, yeah. Okay, I'm back. Sorry, technical glitch. But I just wanted to say that was very insightful. Like you said, a few years ago, maybe this topic was looked upon as a taboo or was not very well accepted. But now people are actively looking into it. And thank you for sharing about your work with SETI. Okay, so the next question that we have here is a very interesting one. It says, what can be a good career path that one can take to become an astrobiologist? It's obviously a very many sciences. You have different aspects coming together for astrobiology. So, what would you think is a good career path to get there?
Yeah, so as I mentioned, there's really so many different fields that contribute to astrobiology. So first of all, I really would go with whatever your passion is, right? So this is maybe like a lame statement or cheesy or cheeky or something like that, but really, it's really do what you're good at and what your passion is. That's half of it. So if you're good in biology at school, maybe think about biology. But if you're good in linguistics, you might even work on languages and be the person who is, the ambassador who talks to the aliens eventually, right? So it's really, there's really so many paths, and this is what for me personally makes also astrobiology so interesting. So it's not only the diversity of the disciplines that come together, but really also the diversity of people who come together. So I think the astrobiology community is one of the most diverse and international and also in terms of gender and social background. So it's a really inclusive community. So the first tip would be really do what you're passionate about and always keep an eye on the connections. So always not be so in many scientific disciplines in general you become a specialist, right? So you focus on one equation you solve, or you focus on one technology that you do in the lab. So in astrobiology, it's really about being a generalist. So coming back to this legend of the blind man and the elephant, you should be able to talk to the other blind man, right, or to the other scientists. So really developing a common language, with other scientists. So me as an astrophysicist, developing a language to talk to a geologist. If you are in linguistics, how can you talk to someone who does machine learning? So it's really, developing these skills to be multidisciplinary. So this is really the most important thing. And then all the rest of the career, honestly, it's also a bit of a lottery. So I'm super lucky and super privileged, and I might have just been at the right time at the right place, and I was probably super lucky to get this flight on Sofia, and I was at the right institute at that time that was working on Sofia. So academia is really a lottery game. So any advice I would give, go to Harvard and then go to Caltech, obviously, but not everyone gets there. So and also, like what many people don't know, most of the people who do a PhD are not staying in academia. So this is like only 10%. If you get a PhD in science, only 10% really stay in academia for the rest of the careers. Most of people, get a PhD and then go into the industry or go into science communication or become journalists or even work in finance or health insurance or something like that. So in terms of career steps, do what you're passionate about, and eventually, your dream might come true. But we like, yeah, do what you love, and then if you're really passionate for it might work out. But be aware of, that it's also a game of luck. So there's no straight path and clear direction to get 100% into academic career. That would be a lie if I can promise you. Sorry.
But that was such a truthful, straight from your heart, but a very motivational answer. Really gained a lot out of it. But so, Dr. Angerhausen, before we move into the meeting room, where I'm sure a lot of our attendees are just waiting to ask you more questions, one question that we ask all our speakers, and we will discuss this in detail in the meeting room too, but I'd just like to ask you here. You are someone who has very actively been involved in science communication. You are training science communicators to do well in the field. I'd like to ask you, what role do you think public engagement platforms such as India Science Festival plays in bringing together science and society? How effective do you think these events are to propagate the cause of getting credible science ahead to the masses?
Yeah, I mean, we're obviously preaching to the choir here because I love doing this and I really enjoy doing it. But I also think it's like super, super important. I mean, we are all aware of the situation right now with fake news and science denialism and ignorance and people having their own opinions, but it's not fact and all these questions. What I advocate always for and what I always try to tell my fellow science communicators is that we shouldn't be preaching, right? So we shouldn't be, okay, this is the truth. So these are the big theorems we found and you have to believe in them. What I really try, and not sure if I was very successful in this talk, but I really want to try is that to make people think like scientists, right? Be skeptical. Like if you read the headline, this is maybe something I can give you on the way. So nowadays, everything is clickbait, right? Even the science news, is there life on planet XY? Probably not, right? So, or, Harvard scientist says there were aliens visiting us, then they just put like some quotation out of a context. So I think being a scientist, and this is maybe one of the big misconceptions, if people see a scientist, they see this old man with the lab coat that tells people what the truth is. But being a scientist is actually being skeptical. So asking questions, is this data right? So if we publish a result, it's always like 99% plus minus one. So we always have to give our how sure we are about our result. If someone says they are 100% sure about something, then they're likely not scientists. So it's really thinking critical, and even your own papers. You're usually, if you're I think most of the scientists are the most critical about their own work sometimes. So really, this critical mindset, really questioning everything. I mean, not being like running around and don't believe in anything anymore, but really, make your own research literally, right? So check your sources, be skeptical. So this is really what this is about, especially in these times today, I think.
Lovely. That was so nice to hear, sir. I completely agree with you when you said it's all about asking questions. And I think that's what all our attendees who are interested in this field and want to pursue it ahead would also take away. The best takeaway from this talk would be to ask more questions and pursue your passion ahead. So I think with that, I just want to thank you. Thank you so much for being a part of our festival. It's an absolute pleasure hosting you at India Science Festival. Thank you for taking out the time and answering these questions. And I'm sure our attendees are just thrilled to ask you more questions in the coming 20-25 minutes. So, sir, yeah, request you to head to the and I will be posting a link for our attendees. So for all our attendees, I'm posting in the chat box. So, Dr. Angerhausen, thank you so much for being a part of this talk. Hope you had a lovely time because we certainly did.
Yeah, I enjoyed it a lot. Please ask me again next time. I'm happy to do it again. This is really exciting.
We would love to host you again, sir. I hope to host you on our on an offline and on ground edition of our festival next time. We hope to see you in
that'd
India.
Be great. That'd be
as
great.
part of our fest.
Good. So I moved to the other Zoom now, right?
Yes. Please do move to the other Zoom room. We'll join you there.
See you there.
Okay, thanks everyone for staying with us so far. I would just request everybody to please move into the meeting room that has been put up in the chat. Please move to this meeting room. We will be allowing only a few attendees to be a part of the post webinar interaction. So I hope you all understand. And I have again put in the link in the chat. So if you could just please click on the chat and move to the meeting room. All right. Thank you so much for staying tuned till the very end. I hope you've had a chance to see the link in the chat box. We'll see you in the meeting room. And just stay tuned. Last few days to go for our festival to end. Really hope to see you all in the coming week, and lots of exciting sessions that we've planned for you all. Keep celebrating science with us because we're here to bring the voice of science to all of you. Thank you so much, and I'll see you. Bye bye.